Previously, we have talked about sequences in general, and then we talked about how we can take the terms in a sequence and we can add them up and form what is called a series. After that, we did a dive into a very special type of sequence called an arithmetic sequence. And the key feature for these types of sequences is that we are going to be adding the same number every time when we go from one term to that next. And that same number that we add every time is called the common difference. We're going to now shift gears and look at a different type of sequence called a geometric sequence. Sometimes it's referred to as a geometric progression. And this can be defined recursively as define the first term to be some real number a, and then to define the nth term that's going to be equal to r times the previous term. That value r is going to be called the common ratio. So the key feature on a geometric sequence is that we are going to be multiplying the same number every time. And how you can figure out what that multiplier is if I take this recursive formula and I divide both sides by a sub n minus 1, I get r is equal to a sub n over a sub n minus 1. So I'll just take the ratio of one term over the previous term, and if you get this consistent multiplier from one term to the next, you are looking at a geometric sequence. So for our first few examples, we are going to just show that the sequence is geometric, and we're going to list the first term and we're going to find that common ratio. In our first example, we have 2, 8, 32, 128, and dot, dot, dot. So to show that this is going to be geometric, because we are given the terms in the sequence, what we can do is just start building some ratios. So if I take the first two terms right here and build its ratio, it would be 8 over 2, which is equal to 4. If I build a ratio with the next two terms, it would be 32 over 8, which is also equal to 4. If I grab the third and the fourth term, its ratio would be 128 over 32, which you can verify would also simplify to 4. So for the terms that we're given so far, we can find then to get from one term to the next term, we're always going to be multiplying by 4 every single time. And because of that, this sequence is going to be geometric. The first term, which you can notate a sub 1 if you'd like, is 2, and the common ratio that you can notate as r is going to be equal to 4. In our next example, we're given our sequence explicitly. So we're told that s sub n is equal to 3 raised to the power of n plus 1. First, let's get that first term. So s sub 1 is going to be equal to 3 to the 1 plus 1 power, or 3 squared, or 9. So our first term is 9. Now to get that common ratio, on this one, don't figure out what s sub 2 is and then just take the ratio like we were doing on the previous example. We're going to find the common ratio using our algebraic expressions. So to figure out what that common ratio is, we're going to take the ratio of s sub n over s sub n minus 1. All right, so s sub n is equal to 3 to the n plus 1. And the denominator s sub n minus 1 is going to be 3. And what this subscript is telling me is in my general expression where I'm seeing n, I will replace that with n minus 1. So up here, then I will have n minus 1 and then plus 1, which was already part of the expression. If I go and clean this up, I'll have 3 to the n plus 1 over, and then cleaning up these exponents, n minus 1 plus 1 just gives me 3 to the n. Right, so now here's where we're going to use our exponent rules. Remember, if you have a to the m over a to the n, so you're looking at a fraction where you have the same base, what we can do is we can subtract the exponents, right? So here I have the same base, which is 3, so I'm going to be able to subtract the exponents, so it's going to be n plus 1 and then minus n. We see that those n's are going to cancel, so you just get 3 to the first power, which is the same thing as saying 3. Right? So with my common ratio, what I'm multiplying every time is 3. Our next example is t sub n is equal to 3 times 2 to the nth power. So I would encourage you to try this one on your own, figure out what the first term is, and then figure out what the common ratio is. And then again, notice on this one, because we're given an explicit expression for that nth term, use that to find your common ratio as opposed to figuring out what a couple terms are and then just taking their ratio. So I would encourage you to try this on your own and then check it against what I'm about to do. Alright, so here we go. I'm going to figure out what my first term is before I figure out what that common ratio is. So I'll have 3 times 2 to the first power. Now be careful with what's going on inside of this expression. We have to follow order of operations. Okay, so 3 times 2 to the nth power is not 6 to the nth power, right? We don't multiply those pieces together. That exponent only affects that base of 2. So after you evaluate that exponential expression, then you multiply it by 3. So just be careful with that. So I'll have 3 times, well 2 to the first power is just 2, and then 3 times 2 is 6. All right, so my first term is 6. Now let's go ahead and figure out what that common ratio r is. So r is going to be t sub n over t sub n minus 1. In the numerator, I'll have 3 times 2 to the nth power. In the denominator, I'll have 3 times 2 to the n minus 1 power. Now immediately I see that these 3's can cancel, so I'll get rid of those. We'll have 2, and then for these exponents, let's subtract them. So n minus, parentheses, n minus 1. Don't forget about those parentheses, because you have to subtract that entire expression that's in that denominator exponent. Distributing through, you'll get in the exponent, so you have 2 raised to the n minus n plus 1. The n's cancel, you get 2 to the first power, which is just 2. So very good. We found out then that the common ratio in this example was 2. And notice in the previous example, the common ratio was 3. So looking at these two examples, if you remember when we talked about the arithmetic sequences, we said a lot of them may look like linear functions structure-wise, and that common difference was equivalent to the slope. Maybe something that we're seeing here is that these look like exponential expressions. And what's happening is that the base of those exponential expressions, or those exponential functions rather, if we think about these as functions, is related to the common ratio. So we'll find then that a lot of our geometric sequences, if we look at an explicit formula, it will mimic what you would see in an exponential function. And for that exponential function, whatever that base is going to connect to your common ratio. So all good stuff. Lots of connections to be made here. We verified that sequences were geometric. Now we're going to explore finding a formula for the geometric sequence. So specifically something for like a general nth term of the sequence. So let's start by building a couple terms in the sequence. Okay, so we're going to kind of verify where this formula comes from. So the first term, a sub 1, I can just write that as a sub 1, right? Nothing special really happening there. But a sub 2 is going to equal r times a sub 1. That's how you build a geometric sequence, is you take the previous term and you multiply it by your common ratio. Obviously assuming that your common ratio r is not equal to 0, because then you don't have anything exciting happening. A sub 3 is equal to r times a sub 2. Right? Just take the previous term and multiply it by r. But a sub 2 is equivalent to r times a sub 1. r times r is the same thing as r squared. So I get here r squared times a sub 1. A sub 4 is equal to r times a sub 3. But what we just found was a sub 3 is equivalent to r squared times a sub 1. Okay, so this r was still sitting here, and I'm going to rewrite a sub 3 rather as r squared times a sub 1. And again, I can combine these r's, and here I get r cubed times a sub 1. So hopefully at this point in time we see enough of the pattern. If not, I would encourage you to build out a couple more terms here. So if I want to find a sub n, a general nth term, what I'm finding in these expressions I'm generating over here is they all will involve the first term a sub 1 somehow. And the other thing that is happening is they will all involve that common ratio r. And if I look at the common ratio r, the exponent on it is always going to be 1 less than whatever position I'm in. So if I'm looking at the third term, the exponent on r is 2. If I'm looking at the fourth term, the exponent on the r was 3. So if I'm looking at the nth term, the exponent on the r is going to be n minus 1. It's going to be 1 less than the position I'm in. And you can either write it like this, or you could put the r to the n minus 1 first, and you can write it then times a sub 1. Right, so the general formula then to find the nth term in a geometric sequence, so the nth term is a sub n is equal to the first term a sub 1 times r to the n minus 1. Let's go ahead and use that formula to find some terms. In this first example, it asks us to find the 9th term of the geometric sequence 3, 2, 4/3, 8/9, and so on. So I know my formula for that for the nth term. A sub n is equal to a sub 1 times r to the n minus 1. I know what my first term is. It's the 3. So I'm going to need that common ratio. So let's go find that first. So my common ratio, if I just want to grab the first two terms, it would be 2 over 3. And there's really nothing I can do to simplify that. So my common ratio is going to be 2/3. This to show you, you could have also grabbed, for instance, the second and third terms. We should still be comfortable working with those fractions. So if I wanted to find the common ratio using those two terms, it would be 4/3 over 2, which is equivalent to 4/3 times 1/2. And I'm going to be able to simplify along this diagonal right here, multiply these fractions, and you still get your 2/3. Right, so that common ratio, it doesn't matter what two terms that you grab, as long as you're building the ratio, you're going to get that common ratio r. Now that I know r, I can put this into my general formula right here, that any nth term, a sub n, is equal to a sub 1, which in this case was 3, times my common ratio, which is 2/3 raised to the n minus 1 power. So that's the formula for the nth term. Let's use it to find the 9th term, a sub 9. So that's going to equal 3 times 2/3 to the 9 minus 1. So cleaning that up, that's going to be 3 times 2/3 to the 8th power. Now, sometimes these tend to get really big, right? Raising things to exponents tend to get rather large. In this case, 2/3 to the 8th power, that's going to actually get rather small. So sometimes for the final answer, we could either leave it like this. Sometimes we can get a decimal equivalent. This, because I'm raising it to the 8th power, is not too terrible for me to compute. So I'm going to finish doing the computation on this. So 3 I'm going to write as 3 over 1, and I would have 2 to the 8th power over 3 to the 8th power. On here, this 3 will wipe out one of these guys' exponents. So then I end up with 2 to the 8th power over 3 to the 7th power. And I would then get 256 over 2,187. So there's the exact answer if I was asked to simplify this. Instead of the 9th term, if I had asked you, for instance, to find the, 115th term, okay, you'd be raising this to the 114th power. That would be kind of big. So this would be kind of a crazy fraction to compute. So there's where I was saying sometimes we might just leave it like this, or we might get the decimal equivalent. So if you're asked for a decimal equivalent, you wouldn't necessarily need to simplify to this fraction. You could pop this into your calculator, and the decimal equivalent to this would be 0.1171. Right, so just pay attention to how you need to express your final answer. One last comment on this before we move on to the next problem is right here where you have 3 times 2/3 to the n minus 1. These pieces right here, do not multiply them. Okay, don't multiply the 3 times that 2/3. I've seen some people on this, if they write it as 3 times 2/3 to the n minus 1, they get kind of distracted that there's a 3 here and a 3 here, and they try to like cancel that, and then they say that that expression is 2 to the n minus 1. Okay, you can't do that. Right? That procedure is not going to work. You have to follow the order of operations. That exponent on that 2/3 is more important than this multiplying by 3. So just keep that in mind for these types of problems, what that exponent is actually attaching to. Okay, so now that we've got that covered, for the same problem, for part B, so same sequence here, let's find a recursive formula for that sequence. So as a reminder, a recursive formula, what that is you're going to first let people know where the sequence needs to start, so what that first term is. And then we're going to say, okay, so then to get to any nth term after that, it's going to be r times a to the n minus 1, r times the previous term. So taking all of that into account for this specific sequence, we would need to tell people where we're going to start, which is going to be at 3, and then any term after that, a sub n, is going to equal to my common ratio, which is going to be 2/3 times a sub n minus 1. So this is just saying you want to get to a specific term, do 2/3 times the previous term. That's it. That's all I have to do for my recursive formula. Okay, so this would be the answer for that part. Okay, now we're going to move into finding sums. Remember that when you sum a bunch of terms in a sequence, that is called a series. The first geometric series that we're going to look at are going to sum through a specific term, so through an nth term. If we have a geometric sequence with the first term a sub 1, the second term a sub 1 times r, and so on and so forth through the nth term, and we just talked about this, the formula for the nth term, a sub n, is equal to a sub 1 times r to the n minus 1. So those are the terms in my sequence, and we want to add them all up and form a series. To condense writing out all of those terms, remember that we can go to our very fancy summation notation using that Greek letter sigma. In this notation, we have to provide a lower and an upper index. So my lower index will usually be 1, so we set k equal to 1, and then we specify what term we want to sum through. If we want to sum through a generic term n, we can just put n up here as my upper index, or we can put a specific number up there, which we'll do on our next examples. We'll specifically sum through the first 8 terms, so my upper index would be 8. Then over here, we write our generic expression for how to generate our geometric sequence. And all geometric sequences can have that generic expression. The nth term is written right here. So all this is over here this is your a sub n, but we've just switched out the variable. As opposed to having n as my variable, we're having k, because we have to connect it back to our index. So the sum of the first n terms can be found by this formula. S sub n is equal to a sub 1 times 1 minus r to the n in the numerator divided by 1 minus r in the denominator, assuming that r does not equal 0 or 1. So r doesn't equal 0 because then we're not really looking at a geometric sequence, right? If I take from my first term and then I multiply the second term times 0, well then that second term is just 0 and every term after that is 0. So it ends up being kind of, there's not even a really sequence there. This formula doesn't allow r to be 1 because if you notice, if we put 1 in the denominator, we would get something that's undefined. So we can't use this formula to sum a geometric sequence if my common ratio r is 1. Let's go ahead and use this formula for the next example. We're going to find the sum of the first n terms of the sequence 3 to the nth power, and then we're going to use that formula to find the sum of the first 8 terms. So in that sequence, 3 to the nth power, my first term, a sub 1, is 3 to the first power, or 3. My common ratio r can be found by doing 3 to the n divided by 3 to the n minus 1. So if I simplify that by subtracting those exponents, we would get 3 to the n minus n plus 1. The n's cancel. We just get 3 to the first power, or 3. All right, very good. So now I have my first term, and I have my common ratio. Let's go ahead and find my sum for the first n terms. So s sub n is given by the formula a sub 1 times 1 minus r to the n divided by 1 minus r. Now I'm going to plug in the values that I have. My first term is 3, and then in the numerator I'm going to get 1 minus 3 to the nth power over 1 minus 3. Because I'm summing through a generic nth term, n will be involved in my final answer. So let's clean this up. So I'll leave this 3 out here in the front for a moment. I'm going to get 1 minus 3 to the nth power, and then 1 minus 3 is negative 2. So maybe as a final cleanup, I'll bring that out in front. So I'm going to get negative 3 halves times 1 minus 3 to the nth power. So there is my generic expression. And again, maybe I'll write a little note here. This will be the sum of the first n terms. This expression will tell me what that sum is. Now it might be helpful for us, because this is the first time that we're looking at these geometric series, is what exactly are we doing here? All right, so maybe let's write out a couple of terms in the sequence to wrap our head around what's going on. The first term in the sequence is 3. If I want to get to any term in the sequence after that, I'll take the previous term and multiply it by my common ratio, which is 3. So that means the second term is 9. My third term would be times another 3, or 27. My fourth term would be times another 3, or 81, and then so on through my nth term, which is given by my beautiful expression, 3 to the nth power. So those are going to be the terms of the sequence through an nth term. We are trying to find the sum of those terms, which means then we're just going to add them all up. And the question is, if you add them all up, what do you get? What we just found over here was the generic kind of expression for how to compute what that sum is. That's what you would get for your sum. So switching this over to a more concrete example, we'll use that formula to find the sum of the first 8 terms. All right, so if I want to find s sub 8, which if I wanted to use my super fancy summation notation, my count is going to start at 1, I'm going to go through 8, and my expression that I'm going to be using to generate my sequence is 3 to the nth power, but remember we've got to connect it back to our index, so it's going to be actually 3 to the k power. Now I don't have to do this to answer this question, but just to write out who is in this sum. So if k is equal to 1, I get 3 to the first power, which is 3. If k is equal to 2, I get 3 squared, which is 9. I'm going to add those up and add up any other term I get after that. If k equals 3, I get 3 cubed, which is 27. Then 81. Then 243. Right, that would be the fifth term, or 3 to the fifth power. then I would get 729. Then I would get 2,187. And then finally my 8th term, which would be 3 to the 8th power, that's where I'm going to stop my sum, is 6,561. And the question is, what do I get if I add up all of those numbers? Now I guess this one wouldn't be necessarily too terrible to just sit here and manually key into your calculator, but the key thing is we don't have to do all of that. We don't have to sit here, find those first 8 terms, and then key them in to add them all up. We can use our formula. And if I'd given you something bigger than the 8th term, if we'd, for instance, gone out into the sequence into the 43rd term, would you really want to sit there, find 43 different terms, and then add all of those up? Probably not. So we can just use our formula right here. So the formula then would be -3 halves, and then 1 minus 3, and then my value for n is going to be 8. So I just need to substitute that in. Cleaning that up, I get -3 halves times 1 minus, now 3 to the 8th power, that's 6,561. And you can just throw this whole thing in your calculator all at once if you want, and I got that the sum was 9,840. So that is the sum of the first 8 terms in my geometric sequence. So this was an example of summing a geometric sequence that was finite, which means it ends at a particular point. In this particular example, I ended after going through 8 terms. We can actually find the sum if the sequence goes on forever. So if your sequence contains an infinite amount of terms, okay, so which means that it'll just keep on going, sometimes that series, remember that all the series is the sum of your sequence, sometimes that series is said to converge, which means it's going to reach a particular number, and sometimes the series will diverge, which means it's just never going to reach a particular number. If we have an infinite sum of the form, so notice this is your geometric series, where there's your first term, every term after that you're multiplying by 1, and this is your generic nth term in your geometric sequence, and you're going to add up all those terms and form a series, and you're going to keep going on forever. You're not going to stop at an nth term, you're just going to keep on adding a bunch of stuff. We can connect that back to our summation notation, but the key thing is because this keeps going on, my upper index is going to be positive infinity. So I'll still start my count at k is equal to 1, but as opposed to counting through a particular value n, we're just going to keep on going. Forever. We're never going to stop. And the cool thing about these is some of these, if we add up an infinite number of terms, some of these will approach a specific number, and some of them will never approach a specific number. And whether or not this infinite geometric series will converge or diverge all relates back to that common ratio. If the absolute value of our common ratio is less than 1, and another way to say that, if r is between -1 and +1, then our infinite geometric series will converge. And we have a cool formula that tells us exactly what it will converge to. That sum is going to be a sub 1 over 1 minus r. So if I know my first term and I know my common ratio, I can figure out what this overall sum is when I sum through an infinite number of terms. Now to me that seems like a crazy idea on the surface, right? I'm going to keep adding a whole bunch of stuff and I'm going to keep adding to it, and you're telling me that I will approach a specific finite value? I would normally think if I keep adding to it, then it's just going to keep getting bigger. And the idea for these is the things that we're going to be adding to it are going to get so small as we go further and further out into the sequence that those infinitesimal steps are not going to make a major difference to that overall sum, and that value is going to be getting closer and closer to a particular number. It's never going to actually obtain it, right, because I'm going to keep adding new terms to it. But the idea is that it approaches this number. And this idea about approaching a number is connected to this idea about limits, which is talked about more in a formal calculus course. Let's take a look at an example of our first infinite geometric series. It's going to be 1 plus 1/3 plus 1/9, and we're going to find the sum of it. So notice it says plus dot dot dot, which means it's just going to continue. This thing's going to go on forever. In order for us to be able to use this formula about finding this sum of this, we need to verify that my common ratio satisfies this requirement about being between -1 and 1. So my common ratio can be found by just taking the ratio of successive terms. So I'm just going to grab the first two terms. So 1/3 over 1, well, that just simplifies to 1/3. So this satisfies the requirement that I can use this formula. In order to use it, I also need my first term. So my a sub 1, my first term in my sequence is 1. Now, I don't necessarily have to write it in the summation notation, but I'm going to because I want to stress how to write it. So we write our sigma. K is equal to 1 is my lower index. The infinity symbol is on the top. And then for this part right here, for my nth term, my a sub 1 is 1 times my common ratio, which is 1/3 to the k minus 1. And if I wanted to, I could clean that up. So I'm going to be going from k is equal to 1 through infinity of multiplying by that 1 doesn't really matter, so I'll have 1/3 to the k minus 1. Instead of writing the series by explicitly listing the terms and adding them up, this is another way that I could present this problem. I could just give this to you using the summation notation. Okay, but in any case, how I find the sum is I'm going to compute a sub 1 over 1 minus r. Right, so this sum is equal to 1 over 1 minus my value for r, which is 1/3. So that's 1 over 1 minus 1/3 is 2/3. So this is 1 divided by 2/3, which is the same thing as saying 1 times 3/2. So I'll get 3/2. That's my sum. So if I add this infinite geometric series, that sum will get closer and closer to the value of 3/2. Notice that there's no variable in the sum. This is what it means for the series to converge. It's approaching a very specific number. So in our last example, what I'd like to do is kind of connect what we're talking about with these geometric sequences to the arithmetic stuff that we were talking about before, and also to remind ourselves that sequences don't have to be arithmetic or geometric. It could be neither. There could be something just totally different going on in our sequence. So let's remind ourselves about how to identify if a sequence is arithmetic or geometric, or perhaps neither. And if it falls into the camps of being arithmetic or geometric, let's find the sum of the first 50 terms, and remember that when you sum a bunch of terms, that is called a series. So in this case, this is going to be a very specific series that's going to go through an nth value. This isn't going to be an infinite series that we're going to create like we were looking at in our previous example. For our first example, we're going to look at 5/4 to the nth power. If you're having some difficulty identifying what type of sequence you're looking at, especially if it's given to you in a formula like this, sometimes it's helpful to write out a couple of terms. So my first term would be 5/4 to the first power, which would just be 5/4. My next term would be 5/4 squared, which is 5/4 times 5/4. My third term would be 5/4 cubed, which is 5/4 times 5/4 times 5/4. So we're starting to get an idea here. Okay, I'm multiplying from one term to the next. I'm multiplying by 5/4. So we're thinking that this is a geometric sequence. And remember how we can verify what the common ratio is by looking at the algebraic structure. So my common ratio, I could find it by doing 5/4 to the nth power over 5/4 to the n minus 1. This is how I can prove what that common ratio is algebraically. So then this is going to be 5/4 to the, subtract these exponents, n minus 1. If I distribute this subtraction through, these n's will cancel. So I'll just get 5/4 to the first power, which is the same thing as 5/4. So this is a geometric sequence with common ratio of 5/4. To find the sum of the first 50 terms, so if I want to write that in summation notation, I'm going to be going from k is equal to 1 through 50 of 5/4 to the k power. I'm going to include in here a little digression about what that formula was. That was a sub 1 times 1 minus r to the nth power over 1 minus r. So for this particular problem, that sum would be my first term, which is 5/4, times 1 minus 5/4 to the, my value for n is going to be 50, over 1 minus 5/4. So let's clean up what's happening downstairs. So I still have this 5/4 hanging out in front. Right here I'll have 1 minus 5/4 to the 20th power, 50th power. And then 1 minus 5/4 is going to be negative 1/4. And then dividing by negative 1/4 is the same thing as multiplying by negative 4 over 1. So I can have 5/4 times, and there is my numerator, and then times negative 4 over 1. And this allows me then to simplify this 5/4 with what's going on in that denominator, right? Because now I'm going to be multiplying it and have everything out on one line. So I'm going to get some nice canceling right there. So when everything's done, this is going to be negative 5 times 1 minus 5/4 to the 50th power. And at this point in time now I feel a little bit more comfortable keying this into my calculator. This is a little bit simpler. So when I keyed this in, I got, oh man, I don't even think I'm going to be able to fit it over here. This is a big number. I got approximately equal to 350,319, and then 0.6161 is what I got in my calculator. Alright, so a pretty big value when I did this through the first 50 terms. Just as a side note for what we were talking about previously, this is a geometric sequence, but if I formed a series from it, that series would not converge because my value for r is not between negative 1 and positive 1. Okay, so this, if I had changed this to an infinite geometric series, it's going to diverge. It's not going to approach a specific value. Alright, so the first example was geometric, and we were able to figure out what that sum was. Let's take a look at our next example. So it's 1, 2, 3, 5, 8. Determine if it's arithmetic. That means you're going to be adding the same number every time. So if I think about this as being an adding relationship, from the first to the second term I added 1. From the second to the third term I added 1. Oh, but from the third to the fourth term I added 2. And then at that point in time, it can't be arithmetic. I don't even need to keep going. So this is not arithmetic, because I'm not adding the same number every time. Am I multiplying by the same time? Well, to get from 1 to 2, I have to multiply by 2. Okay, so if I think about this as being a multiplying relationship, to get from 1 to 2, I have to multiply by 2. But to get from 2 to 3, I would have to multiply that by 3/2. So I'm not multiplying the same thing every time either. So it's not geometric. So this one would be neither. This is actually a modification of the Fibonacci sequence that we talked about previously. It's just missing one of the first seeds, because if you remember, the first two seeds of the Fibonacci sequence are 1, 1. And then to get to every term after that, you just add the preceding two terms. So this is just missing that first one. But to get to this third term, you add the preceding two terms. To get to the fourth term, you add the preceding two terms, and so on and so forth. So this is a slight modification of your Fibonacci sequence. Cool sequence, but not arithmetic, not geometric. All right, for the last example, we're given an explicit formula of n plus 2. If I generate a couple terms of the sequence, if n is equal to 1, you get 1 plus 2, which is 3. If n is equal to 2, you get 2 plus 2, which is 4. If n is equal to 3, you get 3 plus 2, which is 5. And we can keep going, but here's where I'm starting to feel that this is going to be arithmetic. And as a reminder, how do I find that common difference? And generically, using the algebraic expression, you're going to subtract one term minus its previous term. So I'm going to use the subscripts of a sub n plus 1 minus a sub n. And you could do a sub n minus 1. It doesn't matter. We're going to get the same thing. But a sub n plus 1, which means that everywhere in my expression, I'm going to put in n plus 1. So that's going to look like n plus 1 and then plus 2 minus a sub n, which is going to be subtract the n plus 2. If I distribute the subtraction through, and I'm going to purposely not combine those terms, because if you do that, you can see that you're going to get a whole lot of canceling. This n cancels with that n, this 2 cancels with that 2, and here's how I can show generically that my common difference is going to be 1. Alright, so I know I'm looking at an arithmetic sequence, so let's go find the sum of the first 50 terms. So I'm going to need a little bit more space for that. So we'll go over here. So my sequence again was n plus 2. So we want to find the sum of the first 50 terms. And if I wanted to write that in my summation notation, that means I'm going to start at k is equal to 1 through 50 of k plus 2. Now, as a reminder, we had some really cool formulas that told me what these various sums were going to be. And we had some properties that we were able to use. So the first property is I'm going to take this sum and I'm going to break it over two different summations. So I'm going to have the sum from k is equal to 1 through 50 of k plus the sum of k is equal to 1 through 50 of 2. All right, so I'm going to be summing this constant. So as a reminder for the formulas, the sum of k is equal to 1 through 50 of k, generically how we find that is going to be n times n plus 1 divided by 2. And then generically for the second summation I have to do, it's going to go ahead and write that. So summing a constant is just going to be your value for n times the constant that you're summing. So let's go ahead and apply those. So for the first one, it would be 50 times 50 plus 1 all over 2. For my second series, it would be 50 times 2 times my constant. And let's clean this up. So this would be 50 times 51 divided by 2, which is 1275. Adding to that 50 times 2 is 100. So I'll have 1275 plus 100, which is 1375. So that's going to be the sum of the first 50 terms of this sequence. As a final idea, just to maybe wrap up a lot of the different things that we have seen, not only in this unit, but maybe also previously in the course, which I hope highlights the beauty of mathematics and how it's really cool that everything connects. Let's take a look at this series. So the first term is going to be 1 over 0 factorial. The next term is going to be 1 over 1 factorial. The next term is 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, and just keep on going. And we're going to add up all these terms, which means we're going to form a series. So this would be classified as an infinite series. For this one, in order to generate this, we're going to need to start our lower index at 0, which is a little bit different than what we've seen previously, because a lot of our examples we started at 1. But in order to generate this, we're going to need to start at 0. And because this is going to be an infinite series, we're going to go through positive infinity, where a generic term is going to be 1 over k factorial. This series will converge. Right. It will approach a set number, and the number it approaches is really cool and very interesting. So in order to maybe see what's going on, let's write out a couple of partial sums. So as opposed to doing an infinite sum, let's only go out to a specific term. So if I just wanted to sum through the first term, 0 factorial, as a reminder, is defined as being 1, so I would get 1 over 1, which is 1. My second partial sum would be 1 plus, and now I'm going to go through the second term. 1 factorial is also defined as 1, so I'm going to get 1 over 1, which is 1 again. So my second partial sum is 2. My third partial sum would be 1 plus 1 plus 2 factorial, which is 2 times 1, which is 2, so 1 over 2 is 1/2. Now at this point in time, I'm going to stop cleaning these up, and you'll see why in a moment. My fourth partial sum would be 1 plus 1 plus 1/2 plus, and then my fourth term would be 1 over 3 factorial. 3 factorial is 3 times 2 times 1, so that's going to be 1/6. My fifth partial sum, which is 1 plus 1 plus 1/2 plus 1/6 plus, right, so my fifth partial sum, see, my fifth term is going to be 1 over 4 factorial. So remember how you get from 1 factorial to the next one? If 3 factorial is 6, then 4 factorial can be thought of as 3 factorial times 4. Right? Just take your previous factorial and multiply it by the new number that you're including. So since 3 factorial is 6, then 6 times 4 is 24. So this is going to be 1 over 24. And I want to go out one more term. My sixth partial sum, which is 1 plus 1 plus 1/2 plus 1/6 plus 1 over 24 plus, and then 1 over 5 factorial. So 5 factorial is going to be the 4 factorial times 5. So 24 times 5 is 120. So this is going to be 1 over 120. So I think that's going to be far enough out. Let's go ahead and get what some of these partial sums that I haven't actually summed. Let's go ahead and get what their decimal equivalent would be. So the third partial sum would be equal to 2.5. So let's do that in the same color. So 2.5. My fourth partial sum, if you add all of this up, you would get roughly about 2.7. So we'll do 2.67 if I take it out to 2 decimal places. My fifth partial sum, if we add up all of those, this is roughly equal to about 2.708. And then my sixth partial sum, if we add up the terms through the 1 over 120, you get this is approximately equal to 2.717. And what's going to happen is that these partial sums, okay, so these series, if we keep going, okay, and look at the infinite series, just keep computing these out, keep adding terms, they will approach a specific value. And maybe you can kind of already see what they're going to approach. So if I keep going out, and I don't stop at any specific value for n, but I can sum these through an infinite number of terms, this will approach E, Euler's number. Okay. And as a reminder, Euler's number, is approximately equal to 2.718. It is an irrational number, so it does not have a fraction that represent it, right? So the decimal expansion is never ending and never repeating. But while it doesn't have a fraction that can equate to this number, it does have an infinite series that equates to it. So kind of a cool way to connect these series ideas that we've been talking about to something that we've seen previously in the course. All of this is a little bit more advanced in what we're talking about, where in this course we're going to end at looking at specifically at arithmetic series and geometric series. This series is not arithmetic or geometric, but this is what you would do in a calculus course is you start exploring these other types of series and you have to analyze, does it converge, does it diverge, what's going on? And we start exploring some of these other just kind of beautiful and cool properties for how these series can be used to talk about other mathematical concepts. So just an extension idea, connecting a bunch of different things. And then the last thing I want to talk about is that you can really get into looking at sequences and their properties and what's going on. And there is actually a online encyclopedia for integer sequences. It's abbreviated OEIS. Let me just take a moment to spell this. DEGER, there it is, integer sequences. So if you wanted to check this out, you could go to oeis.org and you could type in some of a sequence that you're interested in. So maybe you want to do the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8, and so on. You can type as many terms as you want in that sequence, but the cool thing is that this encyclopedia would look for any sequences that people have added to the database that would have the string of values that you are inputting. And it would tell you about properties of that sequence, if there's an explicit formula that generates that sequence, so all sorts of cool things. So I'd encourage you to go check this out. Type in a sequence of numbers and then see what cool properties and formulas that come out of looking at that sequence.